Okay, it's 5:30 on my clock, so I'm going to start. Hello, everybody. Welcome to my talk about live patching Xenstored. And let me start with introductions. My name is Björn. I'm a principal engineer at Amazon Web Services, and inside AWS, I'm part of EC2's kernel and hypervisor organization, and that means we're responsible for building all the hypervisors running on EC2 servers. And the team I'm specifically on also takes care of security issues at this level, including Zen as well as the EC2 Nitro hypervisor. And that includes us operating tooling and reacting to security issues as they arise. And while we're not doing that, we're also heavily investing into automation around that, because one of the things that you learn early on in EC2 is that it's really, really big, and you have to be working at scale. So just logging in manually into servers and fixing things is not the right thing to do if you're working at that scale. One of the things we want to do for that is we want to be able to automatically end live replace components at runtime, because reboots are exactly the opposite of smooth operations that we're aiming for. Reboots are something that is really, really disruptive to our customers, and they really do not enjoy this. It is also disruptive to our engineers, and probably if you would talk to our servers, they would also tell you that they don't like being rebooted, but rather happily compute on and on. Last year, I talked about one of the building blocks that we use for reliably and automatically replacing components at runtime, and that was live updating QEMU. And if you look a bit further, then QEMU is not the only component inside the Zen infrastructure and ecosystem that you have to be able to automatically update. The next step, if you look at this, are services such as Xenstored, because Xenstored is not restartable. And that means every time you want to ship a new feature or make a bug fix in Xenstored, you will have to ship this new version and you will have to reboot all your servers. And that is, as I said, something that we do not enjoy doing. So what do we do if we want to modify Xenstored? The good news is that upstream Zen these days has a set of patches that enables Xenstored to be live updatable. And that means if you get Zen now, if you build it now and install it now, then you will have a Xenstored version that can be updated. However, that doesn't help you if you've been running an infrastructure for a couple of years already, and there are actually servers that are running with a version of Xenstored that was built a couple of years ago. So unfortunately, even though live update is a pretty cool thing, and it's actually the right thing to do for any component in such an ecosystem, it won't help us right now. So what can we do instead? Can we live patch Xenstored? The good thing here is that we already have some experience with live patching or hot patching system software. And especially if you look at Linux and Zen, we have things like Kpatch and livepatch. And from these tools, we already know which sub-problems we have to solve in order to get this working. But unfortunately, we cannot directly reuse those solutions. So we have to find alternatives for a user space application such as Xenstored. So what do we have to do? So first thing is you have to be able to do binary diffing, because every hot patching infrastructure that people use in production today works on basically the concept of building the original build, patching it, to taking another patch build, and then comparing the two to figure out what has changed. And then you extract the modified functions, put them into some kind of loadable module, inject that into your running system, and make sure that all the code that was originally executing the original code now goes to execute your newly patched code. That is the quintessence of hot patching today. So we need some binary diffing. And given the fact that we will be hot patching Xenstored x86 builds coming from the C version of Xenstored, we can actually reuse the binary diffing tooling that's used by tools such as Kpatch and livepatch. So that's already good news. We don't have to do a lot more there. Then the next thing is, if we do this binary patching, we can figure out the functions that we want to inject into our target. But then we have to have some kind of loadable module, and we need to be able to load this into a running server such as Xenstored. Linux has kernel modules for that. Zen live patching introduced a module loading mechanism to Zen for that. In Userspace, we have to solve this in a different way. Once we solve that, we will be able to inject a module containing a binary patch. And then the next thing is, in order to redirect the execution of the target, we first have to find a place where it's actually safe to redirect execution. And The problem here is that you cannot just go at runtime to any place and redirect execution of a certain function, because that function might just be in the process of being executed, and it's not safe to modify it by having it jump somewhere else or in the middle of that process. So you have to find a spot where this function is not being executed, and kpatch in Linux has a pretty complicated algorithm to figure out when it is safe on a given CPU to make sure that to redirect the execution of the patched function. Livepatching in Xen is a bit easier, but also has to solve the problem, and we have to solve the same problem for Xenstored again if we want to do that. That then will allow us to get to the point where we have to redirect execution. And again, Linux kpatch and Xen livepatch differ dramatically in the solution, and we will see that both solutions don't help us a lot here. And the last thing that we have to do then is we will need to be able to look up symbols in the original Xenstored binary, because a patched function will usually try to access data of the original binary. It will likely call into functions that are in the original binary. So you have to figure out a way on how to get code executed and redirected into the original code again. So these are the subproblems I'm going to talk about today. And let's start with the first one. How do we do user space module loading? And the good news here is, again, this is a problem that has been solved for 50 years or so. We already have the dynamic loader in Linux, and that means we can take a shared library and we can load it into a running program. This is usually something that your running program would trigger itself by calling the dlopen function provided by libdl. But if you do not have that, so if your program such as Xenstored doesn't come with a automated plugin mechanism that does it for you, there are still examples how you would do that by simply injecting the shared library at runtime. And I give two examples here. One is the copy and restore project in Userspace, which tries to come up with a generic way of doing checkpoint restore for Userspace applications and has a tool that allows you to inject shared libraries into running programs. The second bullet point is a GitHub project that has like 70 or 80 forks where people try to build tooling for doing exactly that. And the workflow in both cases is pretty much the same. You use the ptrace infrastructure in Linux to get access to the target process that you want to inject your shared library into. Then you wait for a quiet spot, and I get to what we do in Xenstored for that later. And once you have reached that quiet spot, you inject a bit of code in there. And that bit of code that you inject there essentially does a dlopen of your shared library and an int3 instruction. And then you can ptrace again to execute until you hit this int3. And once you hit this int3, you can have a look at your register state to figure out that the dlopen succeeded or not. And then you know you're done. You can remove your injection code again, and then your program will continue executing. And as long as you did everything right in your redirection, you will actually be executing the patched code in the right places. So that's nice. Now, once we know we want to build a shared library with our hot patch, the next question is, how do we build it? And I already said we reuse binary diff tooling from existing livepatch infrastructures there. And the workflow here is we do actually 4 different builds of Xenstored. The first one is you have to rebuild the original Xenstored from code so that you just get the original binary again. And this original binary will give us the original symbols and addresses that we might use later for resolving external symbols out of our hot patch. After that, we do a second build of Xenstored, but this time we add the -function sections compiler flag. And what this will do is it will ask the linker to generate a Xenstored build where every function in Xenstored is in a separate linker section. And this is something that makes the binary comparison easier in the next step. Once we have that, we do our third build, and that is a build of Xenstored with function sections enabled and with our actual patch in there. And this one will give us pretty much the same as the second build, but with our patch applied. So if we then later compare builds 2 and 3, we will be able to interfere which are the functions that are changed in between due to our patch. And last but not least, we now need to take our patched binary and create a shared library out of it. And in order to create a shared library, we need the code to be position independent. And that is the fourth build that we do, where on top of function sections and our patch, we also add the fpic compiler flag so that the resulting binary is position independent, because only for position independent binaries, you can actually build a shared library in the end. So much for the shared object generation workflow. So we have our 4 builds now, and how do we get the actual binary code to inject into our shared library? As I said, the first comparison we do is between the 2 function section builds, the original build and the new one. And this one will give us a list of newly introduced functions as well as modified functions in our patched binary. And those are the ones that we want to put into our library in the end. This is not enough yet. We cannot just extract the modified and new functions from the patched binary, but we actually have to take them from the position independent binary. This is where the 4th build comes on. And if we do that with pretty much a object copy and a couple of linker commands, we can generate an object file that contains all our functions that we're interested in a position independent manner so that we can build a shared library from that. But they will still have symbols that need to be resolved and that come from the outside, either from libc or from the original Xenstored. And this is where our first build with the original symbols and addresses comes in, because we can then use this build to resolve addresses that are in the original binary and thereby make sure that we can still call functions in the original binary as well as resolve data symbols in the original binary. Okay, and after putting all those 4 builds together in the workflow depicted here, we get a position independent binary as a shared library that has all our modified and new functions and that resolves all the external symbols that need resolving except libc, because libc symbols will be resolved at load time by the dynamic loader. Okay, so now we have our shared library with our hot patch code. What do we do with it? So the first thing is we need to, as I said, we need to bring Xenstored to a place where it is actually quiet and we can be sure that it is safe to apply our hot patch. Xenstored is a really great example or a really great scenario to do this in, because Xenstored is single-threaded, so you only don't have to worry about stopping multiple threads in the same location or in a certain location. And Xenstored, by its very implementation, is a server application. That means there is a main server loop that is listening for events and commands from the outside. And after servicing a current batch of events, the main server loop will get to the same point again. This means we have a point where we know Xenstored will come by every once in a while. And this is exactly the point where it's pretty simple to load a hot patch because we know no other code is executing at that point. And this is exactly what we do. So here's the code that we use for that. We use ptrace continuous syscall, which executes the target program until it executes another syscall. And the thing to know about ptrace syscall here is that it will give you 2 events. The first event will happen once you enter the system call, and the second event will happen once you leave the system call. Now, in our case, when we request Xenstored, we will have to make sure that we don't interfere with the original Xenstored execution. And doing our ptracing until the start of a system call is not safe here, because if we do it at the start of the system call and then inject our code, which again does other system calls in order to, for instance, get the DL open done, then we might lose the result of the system call that Xenstored tried to do originally. So what we do instead is we wait for the end of the system call. Because at the end of the system call, we know the kernel did everything that might have side effects in the kernel and just returns to Userspace. And this is a safe place where we know we can resume from here later without interfering in Xenstored execution. Now, the question is, which system call do we wait for? And as we see here, we're actually waiting for the poll system call. This is because Xenstored is using poll, or it is using select, which in turn uses the poll system call to achieve its goal. And this is the one place where in the main server loop, you have a select call, and this will end up calling poll. So that's, if you see a poll from Xenstored, you know this is the only place where it can come from. And if you see this is an exit from a system call, you actually reach the quiet spot and you can now proceed loading your hot patch. So let's move on. What do we do next? The next thing is we execute our injected code, as I said in the beginning, and that injected code will call DL open on a hot patch library. And this hot patch library comes with a set of constructor functions. And the first constructor functions that's being executed is there to redirect control flow of the actual hot patch functions. So we know the list of functions that we need to hot patch. We know their addresses because we pulled that list from the original Xenstored build that we looked at. And now the question is, how do we do code redirection? And the simplest thing to do would be to override the patched function with a jump to the address of our new function. And this is actually what, for instance, Xen livepatching does. And unfortunately, that does not work for Xenstored. And the reason for that is that a jump on x86-64 has a 5-byte opcode. And that's 1 byte for the actual jump opcode and 4 byte as an immediate for the relative jump that you want to do. And unfortunately, with the 4 byte immediate, you can only jump plus or minus 2 gigabytes from your current location. And if you have a look at the address space layout for regular Linux applications, then you will realize that shared libraries are usually way more than 2 gigabytes away from the original binary loaded binary. So we cannot use a jump. Luckily, we are on x86-64. So if you can't use a 4 byte relative jump, let's just do a 64-bit direct jump. That works as well. So we can just take the source function, we override it with a move absolute of our hot patch address to RAX, and then do a jump through RAX. That would work. Unfortunately, you have to be careful here because we're patching code more or less live. And if your code adheres to standard calling conventions, then overwriting or tainting RAX at the start of a function is actually safe because the standard calling conventions say that RAX is used for the return value of a function, which means every caller for a function would have to store previous values of RAX before calling into a function, because that function would then override RAX anyway. And if we override it before that with our jump and use it for the jump, that might work. Unfortunately, we cannot rely on all our functions that we ever want to hot patch to be compliant with calling conventions, because C has this nice thing called static functions, and static functions allow the compiler to do optimizations. And one of the optimizations would be inlining functions, which is not necessarily a problem for hot patching, because that will just mean you have multiple modified functions based on a single modified inline function. But another thing a compiler can do is it can have a look at the caller and the callee of a function, figure out that, for instance, this function doesn't have a return value, so it doesn't have to store RAX before calling the new function, and then it doesn't have to restore anything. And if you hit this kind of case, then overwriting RAX is actually unsafe because you might be overwriting data from the original program. And so if you wanted to use a move ups and a jump to RAX for hot patching, you could do so, but you would have to carefully analyze every place where your functions, your patched functions are called in order to make sure that it's actually safe to override RAX. Luckily, we found a different alternative that doesn't require us to go through all the functions manually, and that is borrowing some idea from the Red Pauline runbook. And that is, instead of doing a jump or a call, we patch our patched function with a push of the target address of our function of a hot patch function, and then use a ret to actually redirect execution there. And that works because if you look at it, that's pretty much the same thing as doing a jump to a function. It is just not tainting any registers, but just using 8 bytes on the stack. And this is pretty nice, and this is what we're using for redirecting control flow. And with that, we now have a mechanism to generate a hot patch shared library from a binary diff, to query Xenstored, and at load time to redirect all the Xenstored functions that we want to redirect into new locations. That is cool. So the last thing we have to solve here is dynamic libraries and symbol resolution. And if you know something about dynamic libraries, then you probably already know that they are placed at random locations in the address space based on address space layout randomization and based on what the dynamic linker will choose. And one thing the dynamic loader does when loading a shared library is to figure out what external symbols need resolution. And in our case, for instance, our hot patch will come with code that calls, for instance, into libc, and we don't carry the printf function, for instance. So it will have to be resolved from glibc, which is also loaded somewhere in the address space. And this is where the global offset table and the procedure linkage table come in, the GOT and the POT. And actually, the GOT is the interesting part because the GOT is the list of addresses to external symbols that need to be resolved, and it is filled by the dynamic linker at load time of your shared library. LDSO does so by looking up the external symbols in the list of symbols exported by libraries and binaries at link time. Unfortunately, that requires you to build your library or your binary that you want to call into with the rdynamic flag to the linker. because then all the public symbols will be exported and LDSO will be able to find them at load time. This works pretty well for the glibc. So when we load our hot patch and have references to the glibc, LDSO will figure out where they are, put them into the GOT for a hot patch, and we're done. Xenstored, unfortunately, is not built with -r dynamic, so we do not have any information about the location of symbols in Xenstored at load time. That means we need to solve that problem beforehand. And we do that as part of our hot patch build process and essentially leverage GNU-LD's --defsim flag here. And --defsim in GNU-LD allows you to define an arbitrary symbol with an arbitrary value, which is an absolute value. And what we do here is we do an nm call on the hot patch to figure out which are the unresolved symbols. Then we do an nm call on Xenstored, which contains the symbol addresses still in the original build. And then we match those. And if we find a symbol that the hot patch requires and that is in Xenstored, we use nm on Xenstored to actually look up the address of the symbol. We define it in the hot patch with --defsim, and that will make it part of the GOT and resolve the address at link time already. This is all nice until you start loading your hot patch. And it's something we didn't expect when it happened, but what's happening at load time is LDSO relocates your library. And imagine you build your hot patch and you use the trick with --defsim to have a static pointer point into some place in Xenstored. What now happens is LDSO takes your hot patch and relocates it to a different location in your address space. And unfortunately, the GOT entry that you created with --defsim is actually just an offset from your GOT to Xenstored. And by relocating your shared library, that offset is no longer valid. So what's happening here is LDSO is actually relocating that for you. And that is a problem because with the trick that we used at link time, we actually defined absolute values and we know where in Xenstored we want to jump, and we do not want LDSO to fix that up for us. So what we have to do is we have to revert that, which means we now have a GOT in our hot patch that has addresses into Xenstored where we know the absolute values and we know we want them to be at specific values, but unfortunately they are relocated at load time. So what do we do here? We have to somehow identify those GOT entries in order to distinguish them from other GOT entries that really need this relocation by LDSO. And we do that by transforming the addresses at link time into addresses that are non-canonical. And we do that by turning on the top 4 bits of the address of a 64-bit address. Those give you addresses that will never, ever be valid on a Linux x86 64 system, and therefore can be identified as, hey, this address has been marked as a specific address that needs or undoing of the relocation. And this is the second step that we do. In our constructor at load time, before we start redirecting any calls, we unpatch or unrelocate our GOT entries, which is we have a loop that goes over all the GOT entries in our hot patch library. And if you find those that have our hot patch address mask set, which is these top 4 bits in the 64 address space, what we do is we remove those top 4 bits because we know those are never valid. And then we also subtract the base address that our hot patch got loaded to. And thereby we fix up the GOT entry to point to the real absolute location that we want to point to in Xenstored. And thereafter, any access from the hot patch to Xenstored will go to the valid address. So that brings me to the end of my talk already. So the conclusion is, with the steps I described in this talk, we are actually able to load hot patches into user-space applications, such as Xenstored. And the sub-problems we have to solve there is we have to use or generate binary diffs, because this is what we need for generating a hot patch from a binary. And the good thing here is that we can actually reuse existing tools. For module loading, we use shared libraries because this is the standard way of injecting code into running Linux applications. We need to think about quiescing, and the nice part here is that we can leverage knowledge about the target program, and that Xenstored actually lends itself to easily find such a quiet spot where it's safe to apply a hot patch. And then we have to redirect execution, and we figured out that push and return is a pretty good idea because it allows us to redirect execution without tainting any registers, which might cause hassle otherwise. And in order to properly implement symbol lookup in the original binary, even if the binary does not provide you information at runtime, we use a combination of link time tricks and load time massaging of the global offset table in order to get the right symbols done. And with that, I'm done, and I'm happy to answer your questions. Thank you very much. Thanks for asking a question, Norbert. So question is if there are any lessons learned for other hot patching other user space applications. And the answer is yes. I think the workflow that we present here is pretty much applicable to any other user space application. The binary diffing will be the same. Module loading with a shared library is also generic on any Linux or Unix system. Execution redirection via push and ret will work, and the symbol lookup is also working good enough. So in the best case, your original application is already built with -r dynamic, then you will not have to do any tricks. Otherwise, our symbol lookup mechanism is also applicable to anything. The one thing where you will have to figure out things yourself, depending on your target program, is where do you find the quiet spot to actually apply your hot patch? And this highly depends on what your target application does. And I imagine it will be pretty interesting to find such a spot in something that is, for instance, running with hundreds of threads, where you have to make sure that none of the threads is actually executing the target. But you may be lucky again if you, for instance, know that those threads are worker threads executing a certain worker function and nothing else, then you can still apply your hot patch, but this is really highly dependent on the target application. All right. I think it's time for the next talk now. Thank you all very much for being here, and see you all later.